All right, moving on with regression. We last left off with talking about a plot of an experiment where we had frequency of brushing, number of times a week that we brushed plants to try to keep them small, and then a response variable of height. Okay, and we said that regression was for experiments with a continuous independent variable or treatment variable. 0, 1, 2, 3. Whenever you can line things up like that, you have a continuous variable. Time is the ultimate continuous variable, right? If I had number of days or hours of the day, time is the ultimate. So that's a good chance to use regression. And now we want to test the null hypothesis that all the treatments are the same. Okay, that is what the computer always does. And Excel being no different. In other words, another way of saying that all treatments are the same, our treatments are 0, 1, 3, 4, and 5. So 0, 1, 3, 4, and 5 is, what would this line look like? Think about what this line would look like if all the treatments were the same. Well, the height would be the same, and so we would have a horizontal line. So what we're really testing when we do regression, which we'll do now, is the question, is the slope 0? That's what the computer is going to do. Is the slope 0? And, if so, what's that probability that it is? So let's go to data analysis. There is only one regression in Excel, so we'll go down here. It wants to know where the y range is. The thing on the y-axis, is your response variable. I'm going to go and grab that data for it. Now it wants to know where the x is, because we've got to do this on xy pairs. I'm not going to check the labels box because I didn't use the labels. Okay, so I'm not doing that. And then the other thing I need to do is to give it an output range. I could check some of these, but that's beyond what we need to be doing. So I'll click in the box and I'll go out to the right here and say OK. Now the plot has already given us about everything that we ever want to know. Okay, and we get some of that repeated. We get the same r² value here. We can see the slope down here. We could see the intercept here. Great. We already knew that. What we don't know is what's the p-value? What's the probability that the slope is 0? And all that is right here. So, in fact, we can test the intercept too. Not that we care about that all that often, but so here's our p-values. The x variable is also the slope. Again, 8.2. Go back and check. There's the 8.2. Okay, so a very remote possibility, 1 times 10 to the minus 13th, that slope is 0. Okay, so we would conclude it is non-zero. Okay, the minus 8.2 is the real deal. It is not the same as running a flat line through these data. It is in fact a downward sloping line. And we also can say without doubt that the intercept is non-zero. If here's the origin here down here is the, what we're saying is that the 71 value, which is shown in the equation here, definitely doesn't go through the origin of this plot. Okay, big deal. We know that the plants get smaller as you brush them. Now let me just show real quick with a little bit of time left is what this actually means and the predictive capability. Notice that we didn't do 2 times a week in this experiment. Okay, but just because we didn't do it doesn't mean we can't actually project what would have happened had we done 2. We have a nice equation. We have an r² that tells us that the line fits the data actually very well, explains a lot of the variance in it. And if we plug 2 into this, so we get 2 times 8, about minus 16, plus 70, that's going to be about minus 54 or something like that, right? Yeah, and if we go up from 2, don't we hit the line? Right about there, where it should be? Sure. So we can actually predict to a grower, even though we didn't do 2 in our experiment, what would have happened likely if we had done twice a week. And so that's the power of regression, is being a little bit predictive on that. Now I want you to predict what would happen if we did it 10 times a week and then try to explain why you get that answer.